Hi, my name is Arnaud Thernisien. I'm a research physicist at NRL, the US Naval Research Laboratory in Washington, D.C. My colleague, Dr. Damien Chua, will join me later through this talk. We both work in the solar physics branch of the Space Science Division of NRL. In this video, we will talk about the Sun, the solar atmosphere or corona, and how the solar activity is the source of various phenomena and disturbances here on planet Earth. Everyone knows the Sun. It's the source of life on our planet. It is seen here in the visible light. The Sun's surface has a temperature of 5,800 degrees Kelvin, or about 10,000 Fahrenheit. If you use special glasses, such as the one used during solar eclipses, you can observe its surface and you might distinguish some dark spots. These spots are the results of strong magnetic field regions. The Sun's magnetic field is generated by the dynamo effect, the same effect that produces the Earth's magnetic field, but with a way stronger and complex in the case of the Sun. If you look with a special red filter in the so-called H-alpha, which is typical of the hydrogen atom, you might also distinguish some prominent structures hanging slightly above the surface. Now, if you are lucky enough to be at the right place at the right time, you might be able to witness a solar eclipse. This happens when the moon is perfectly aligned with the Sun and the Earth, and it casts a shadow on the surface of the Earth. These amazing phenomena are very local, only last few minutes, and occur very rarely, roughly every 18 months. Eclipses reveal the atmosphere of the Sun, also called the solar corona. It is made of a hot ionized gas, or plasma, that has a temperature of about 2 million degrees Kelvin, or 3.5 million degrees Fahrenheit. The corona appears highly shaped, as you can see in this image. The free electrons of the plasma follow the magnetic field of the Sun, just like iron filings would when placed near a magnet. The solar corona is shaped by the magnetic field of the Sun. The furthest we can see during eclipses is a little bit more than 3 solar radii. So to sum up, these phenomena are not only rare and short-lived, but also offer a limited view of the corona. The corona has two components named K and F. The K corona is due to Thomson scattering of the sunlight by the electrons of the coronal plasma. The K corona is shaped by the magnetic field of the Sun and can vary quickly. On the other hand, the F corona is due to the mis-scattering of the sunlight by the dust cloud surrounding the Sun. It is not shaped by the magnetic field and does not vary. The F corona is also called the zodiacal light. Last thing, the corona is optically thin, meaning we can see through it. This fancy and old plot that I will show here gives the brightness of the corona versus the distance to the Sun. Both axes are in log scale. What that means is that if I take the brightness of the vertical axis, for example, each number corresponds to a factor 10 drop in the brightness as you get further away from the Sun. At the top, the horizontal blue dashed line gives the brightness of the blue sky during the day. The corona is a way dimmer compared to the blue sky, which explains why it is not visible during the day. On the other hand, during eclipses, the blue sky background drops by a factor 1,000, and therefore the corona is revealed. In 1930, Bernard Lyot, a French physicist, invented an instrument that could create an artificial eclipse of the Sun. For the first time, This allowed the observation of the corona for hours long instead of few minutes. These observations revealed that the corona is active. As you can see in this movie, you see some activity just above the sun limb. Bright and dynamic structures called prominences were observed moving and levitating above the solar limb, and sometimes seemed to be ejected away from the sun. Note that the movie here has been accelerated by 600 times. A little bit of optics in this slide. This diagram shows the principle of LEO's coronagraph. The lens O1 on the left focuses the sun on the occulter disk D1. This occulter disk blocks the direct sunlight and sort of acts like the moon in an eclipse. The internal aperture A1 and spot D2 are there to suppress the stray light due to the reflections, scattering, and diffraction of the A0 aperture and O1 lens that sits in direct sunlight. Finally, the lens O3 creates an image of the corona on the focal plane F, where a picture of the corona can then be taken. Later, in 1940, during World War II, Walter Roberts used LEO's coronagraph at the Fremont Pass near Climax in Colorado. He observed that the changes in the corona affected the radio communications and concluded that these changes could provide advance warning of communication disturbances. This became important during World War II wartime security. The Harvard College Observatory work pursued by Roberts was classified and overseen by the Navy during this period. Note that the Harvard College Observatory was soon after renamed High Altitude Observatory. You can observe here in one of his movies an amazing eruption shaped in a magnetic structure reminiscent of a so-called flux rope. Once this structure leaves the field of view of the instrument, there were no means to follow them further away from the sun at that time. This image, which is taken in ultraviolet light, shows the scale of the phenomenon compared to the size of the Earth. The Earth is a tiny little thing compared to the size of the sun. And of course, the Earth is much further away from the sun in reality. This is just for perspective here. Back to my old-fashioned plot here. The only way the corona can be observed further away from the sun is to get rid of the blue sky or air scattering. And this is done by sending coronagraphs in space. And this is what was done in the 60s, either by using balloon-borne platforms or sounding rockets at first, and then with satellites after 1965. One takeaway from this slide is that making coronagraph is not an easy business. As the scientists, as you can see, had to wait for the 70s, one decade, to finally identify a coronal mass ejection propagating further than only few fraction of the solar disk distance. For the first identified CME, the legend says at NRL that Dave Roberts, an electronics technician working for NRL who had been responsible for the testing of the coronagraph's camera, was in charge of day-to-day operations. He thought that his camera had failed because certain areas of the image were much brighter than normal. But on the next images, the bright area had moved away from the sun, so he immediately recognized that as being unusual and took it to his supervisors, Dr. Bruckner and Dr. Toussey. This observation finally unified our understanding of various coronal transients as all being separate parts of the same physical phenomenon. Skipping some years ahead now, one breakthrough instrument by its image quality and longevity is the LASCO coronagraph on board of the SOHO mission. SOHO is a joint ESA and NASA mission, and it was launched at the end of 1995. The LASCO coronagraph is still functioning as we speak. As a matter of fact, NOAA is still relying on LASCO data for space weather predictions. The 27 years of almost uninterrupted LASCO observation of the corona is unique and precious. It allowed many breakthroughs in the understanding of the physics of the corona. Here, a sample movie obtained by the LASCO coronagraph. This is a composite of LASCO C2 for the inner field and LASCO C3 for the outer field. In the movie, on October 28, 2021, you can observe a so-called halo CME. A halo describes the shape of the CME in the image. Its leading edge seems to propagate in concentric circles centered on the sun, like this. These kind of CMEs are generally directed towards the Earth and can cause various disturbances that we will explain later in the video. Note also the random saturated noise that looks like snow. These are energetic particles coming from the sun and impacting the image plane of the camera. Other more recent mission observing the sun, the NASA stereo mission, was launched in 2006. The concept was to have two identical spacecraft. One was sent on orbit ahead of Earth, the other behind. Both spacecraft drifted by 22 degrees per year in each direction. The idea was to observe the sun and its corona from two separate viewpoints to allow stereoscopic reconstruction of the corona and triangulation of the CME trajectories. Stereo has on board the SECI suite of instruments that has two coronagraphs, Core 1 and Core 2. Note that Stereo has on board another sort of coronagraph called heliospheric imagers, or HI. These imagers are not directly pointed at the sun like coronagraph. They instead look on the side much further away from the sun. Here on the top row of this slide, you have the stereo behind images of the CCOR 1 coronagraph, the Core 1 coronagraph, Core 2, then HI1 and HI2, which look on the right side of the sun. The bottom row shows the stereo ahead images in the reverse order, and this time the HIs look on the left of the sun. The heliospheric imagers allow tracking CMEs beyond the field of view of coronagraphs. And in the case of stereo, they could see the CMEs propagating up to the Earth, as I try to show here in this slide. Here is an example of several CMEs observed by both CCOR Core 2 behind and ahead. The separation between the two spacecraft was 130 degrees. These stereoscopic observations allow much more precise determination of CMEs and transient direction. On the right, we show the direction and speed of 24 events determined using the CCOR 2 stereoscopic images. Well, it is time to conclude the first part of this video. To sum up, the solar corona is sporadically observed during eclipses, but can be continuously observed using spaceborne coronagraphs. The sun and its corona is active. Its activity is mostly governed by the magnetic field of the sun. Coronal mass ejections are transient magnetic structures that can be directed towards Earth and are the source of various phenomena and disturbances. This is what my colleague Dr. Damien Chua will address in the next part of this video. Thank you for your attention and stay tuned.
Thank you for the great introduction to the solar corona and the observations that have helped us understand the basic physics and phenomenology of this region of the sun. My name is Damien Chua, and I'm a research physicist at the Naval Research Laboratory in Washington, D.C. To review, the observations made by coronagraphs have shown us that coronal mass ejections are transient outbursts of solar plasma and magnetic fields. Near the sun, they have a scale size of several solar radii. But as CMEs propagate outward through interplanetary space, they expand, and at the distance of Earth's orbit, they can be as large as a quarter of the ellipse encompassed by Earth's orbit. Their speeds range from about 200 kilometers per hour on the low end to as high as 3,000 kilometers per hour for the fastest CMEs that we've observed to date. This means that it takes CMEs anywhere from a few days to about 15 to 18 hours to travel to the distance of Earth's orbit. CMEs propagate outward faster than the background solar wind, meaning they're plowing through the medium in which they're traveling faster than the medium itself. This creates a shock near the leading edge of the CME that accelerates particles to high energies within the structure of the CME. CMEs travel in all directions around the sun, but given their scale size, many of these CMEs do hit Earth, and when they do, they can have significant impacts on the space environment around Earth on a global scale. Earth's own magnetic field creates a bubble around our planet called the magnetosphere that usually limits the entry of the solar wind to regions closer to Earth. However, when CMEs impact our magnetosphere, our magnetic bubble is compressed, and this creates a global scale perturbation to the particles and fields that exist within it. Enhanced electric and magnetic fields in our magnetosphere create highly structured plasmas or collections of charged particles within our magnetosphere and our ionosphere, the portion of our upper atmosphere dominated by charged particles. We also see enhanced fluxes of high-energy charged particles in the Earth's radiation belts. And during CME events, energetic solar wind particles have a greater degree of access to directly enter our upper atmosphere over the polar caps. Another telltale sign of disturbances brought by CMEs is enhanced auroral activity at mid and lower latitudes that you'll often hear in the local media and news reports and weather forecasts when this is happening. We now know that CMEs are the primary cause of geomagnetic storms and space weather at Earth. Global scale signatures of geomagnetic storms include the enhancement of a ring of current that flows around the Earth near the equator. This ring current, along with contributions from other storm time current systems at low and mid latitudes, is observed on the ground as an enhanced horizontal component of the magnetic field measured at Earth's surface. If you recall from Faraday's law from freshman physics, you'll realize that changes to the geomagnetic field will induce electric fields at the Earth's surface. These give rise to the flow of electric currents anywhere where a conducting path might be present near the Earth's surface. These are known as geomagnetically induced currents, and we'll come back to those in a moment. So remember that CMEs drive a large-scale reorganization of charged particles in the Earth's environment during geomagnetic storms that they create. And in the Earth's upper atmosphere and ionosphere, we observed enhanced electron densities and total electron content in a mid-latitude band on both sides of the magnetic equator, as seen in this composite image of the ionosphere from NASA's TIMED satellite. You'll also notice that embedded within these regions are smaller scale structures called plasma bubbles, which are areas of plasma depletion that are caused by instabilities within the plasma. This highly perturbed structure of the ionosphere creates problems for anyone or anything that would like to pass a radio wave from below the ionosphere, say from the ground, to a point above the ionosphere, for example, to a GPS or communication satellite in space. And indeed, these plasma bubbles that we see here are strongly associated with the phenomenon known as radio frequency scintillation. The errors induced on radio frequency transmissions are one of the most significant hazards associated with space weather. Geomagnetic storms are known to introduce errors to navigation systems like GPS, as well as blackouts for high-frequency radio communications. Two well-known incidents of this nature include the FAA's Wide Area Augmentation System going down during the so-called Halloween storm of 2003, and a large-scale diversion of flights away from polar routes during a magnetic storm in January 2005 due to high-frequency radio blackouts at high latitudes. Geomagnetic storms can also have devastating impacts on satellites themselves. During such storms, the upper atmosphere is heated, and we know that when a gas is heated, it expands. And in the upper atmosphere, this increases the density of particles at higher altitudes compared to normal. So low Earth orbiting satellites that then pass through this expanded upper atmosphere then experience more drag, which subsequently alters their orbits with potentially bad consequences. So during the Halloween storm of 2003, there was a period when the locations of a majority of low Earth orbiting satellites were temporarily lost due to drag-induced errors on their orbits. And it became a significant effort to reacquire tracking of all of these satellites. More recently, SpaceX lost almost 40 of its Starlink satellites on February 4th, 2022, when a higher than anticipated atmospheric density was present during their deployment during a geomagnetic storm condition. So all told, these space weather effects present clear and present risks to billions of dollars of commercial activity and civil infrastructure. So to better understand the need to identify and forecast threats from CMEs and space weather, let's consider this tropospheric weather analogy. So consider a situation where we didn't have all of the great assets that NOAA deploys to observe the Earth and its weather systems. In this situation, we wouldn't have any advance warning of large-scale threats posed by hurricanes and tropical storms until they made landfall, which by time it would really be too late to mitigate against the damage associated with these storms. But in reality, we know that geostationary imaging provided by NOAA's GOES satellites provide early identification and detection of hurricanes, analogous to the capability that coronagraphs provide for CMEs. And then when we combine that capability with forecast models and additional measurements, the GOES imaging provides critical observations that enable the prediction of storms and the creation of actionable forecasts to mitigate their worst effects. So when we combine coronagraph imagery with space weather forecasting models, we hope to provide the same capability for space weather. So at NRL, our heritage of building research-driven coronagraphs led us to pursue transitioning these technologies for operational use. In 2010 and 2016, NRL submitted a concept study report to NOAA for a coronagraph design that would make it easier to deploy these on a wider variety of spacecraft. Thus was born our Compact Coronagraph, or CCOR instrument. In comparison to a conventional LEO coronagraph like Core 2 on stereo, the CCOR design is roughly half the size, which makes it much easier to accommodate either as a rideshare payload or a primary instrument on a small, dedicated space weather mission. We applied first principles understanding of Fresnel diffraction physics with some creative optomechanical engineering to create a coronagraph design that achieves the same level of diffracted stray light or background rejection as stereo Secchi Core 2, but with far fewer optical elements and at half the size. So we basically threw out many of the internal optical elements of the LEO coronagraph and replace them with with a single multi-disc occulter as shown here on the right. NRL is currently building or developing 3 CCORs for operational use by NOAA. CCOR 1 will fly on the NOAA GOES-U satellite at geosynchronous orbit and is anticipated to launch in April 2024. The second CCOR, or CCOR 2, will fly as one of the primary payloads on NOAA's Space Weather Follow-On, or SWIFO spacecraft, to the L1 Lagrange point. The L1 point lies along the Sun-Earth line, where the gravitational pull on an object is balanced between the Earth and the Sun, meaning one can park a satellite there in a stable orbit, making it a very ideal point to make solar observations. SWIFO L1 and CCOR 2 are expected to launch in early 2025. We're also in the early stages of development of CCOR 3, which will be NOAA's contribution to the European Space Agency space weather mission called VIGIL. VIGIL will observe the Sun-Earth line from the Lagrange L5 point, which is 60 degrees off the Sun-Earth line, trailing the Earth's orbit. And VIGIL is estimated to launch in the 2029 timeframe. So here's a more detailed view of the CCOR instrument on GOES-U. This cutaway diagram shows the inner workings of CCOR 1. From the front, sun-facing end of CCOR, we have an aperture door that can be reclosed if necessary to protect the instrument. You can also see the multi-disc external occulter, which is the device that blocks out the bright disk of the sun. And next we have the lens assembly that focuses the scene onto the detector, which then collects the images. So we've delivered CCOR 1, so the GOES-U spacecraft, in late January of 2022. And here you can see it being installed on the GOES-U solar planing platform, which is the deck where all of the solar observing instruments are mounted on the spacecraft's solar array yoke. In addition to the hardware, the CCOR team has been preparing for the processing of CCOR data by simulating the images that CCOR will produce. This is a simulation of the CCOR imagery that is produced by scaling real LASCO C3 coronagraph images to the brightness that we expect from CCOR data. This simulation shows us that CCOR will readily detect CMEs within its field of view. NOAA will use CCOR data to derive a number of parameters for each coronomass ejection detected. These include the CME velocity, including its speed and direction, the width of the CME, and an estimate of the CME's mass based on the brightness of the structure in the CCOR images. So these two stereo Core 2 images give an example of how the CME speed is estimated from the coronagraph images. This is calculated simply as a difference in radial position of the CME front from one image to a subsequent image, and then dividing by the time interval between the images. NOAA will use CCOR images and the CME parameters derived from them as input to the solar wind and heliosphere model being run by their Space Weather Prediction Center in Boulder, Colorado. This is the WSA NLIL model, which can be used to produce forecasts of CME arrivals at Earth. This model can be used to issue geomagnetic storm watches and warnings that are broadcast to more than 50,000 unique users through their web interface. For more severe storms, NOAA contacts power grid operators and FEMA directly to coordinate responses as needed. It's been demonstrated that including coronagraph observations of CMEs into the space weather forecast models has improved the success of their predictions from 27% to 60%, and that the window of uncertainty as to when they'll arrive at Earth is reduced from 12 hours to 7.5 hours. This table shows some of the performance requirements levied to us at NRL from NOAA for the CCOR design in order for our coronagraphs to provide the data needed for these forecasts. CCOR will observe the solar corona starting from about 3 solar radii out to 22 solar radii. And the images will be taken every 15 minutes, which will allow NOAA to track CMEs with speeds between 200 and 3,400 kilometers per second. The last row of the table here is worth noting. We will be able to measure the corona at a brightness level 11 orders of magnitude dimmer than the mean solar brightness. That shows how dim our signal is compared to the scene that's in our field of view. We essentially have to turn the sun off in order to see our target signal. CCOR-1 will observe the solar corona from geosynchronous orbit. When SWIFO L1 launches, we'll add another point of observation from the L1 point. Vigil and CCOR-3 will add a different side-looking perspective from L5. And we've learned from Stereosecchi that multi-point observations of the corona and CMEs greatly enhances our capability to accurately characterize their properties. The 3 CCORs working together will be able to triangulate the speed and direction of CMEs with greater accuracy than a single coronagraph alone, which in turn will improve the accuracy of space weather forecasts at Earth. Here's a quick view of CCOR-2, which is currently going through environmental testing at NRL. We're scheduled to deliver CCOR-2 to the SWIFO L1 spacecraft in a few months. And here's a quick peek at CCOR-3, which is in the early stages of its development with our partners at ESA for the Vigil mission to the L5 Lagrange point. So here are some takeaways from this presentation. CMEs are commonly observed phenomenon in the solar corona, and many of these can be directed toward us at Earth. CMEs are responsible for driving geomagnetic storms and their associated space weather effects that threaten critical infrastructure on which society functions. These can include our power grids and any assets operating in orbit around Earth. Space-based coronagraphs provide an early warning capability for the detection of CMEs. And NRL has been successful in transitioning our expertise in coronagraph development from the research world to operations. And finally, we're looking forward to continuing our partnership with NOAA to utilize CCOR to enhance our space weather forecasting capabilities. So thank you for listening. And if you have any more questions or want to learn more about the solar corona and coronagraphs, here are some places on the web where you can go to get more information.